Yeah, you can start whenever you want.
Sure. You can see my screen, right?
Yes.
Give me a moment.
It's also on YouTube.
Okay. I think I'm ready.
Perfect.
So can I start, right?
Yes.
Great. Okay. Welcome to my presentation about our paper. In this work, I will present the nonlinear representation dilemma. Is causal abstraction enough for mechanistic interpretability? Please feel free to ask questions anytime during the presentation and do not hesitate to interrupt me. I will begin with a brief introduction on causal abstraction. Great. Let us start by having some task for which we present the assumed underlying algorithm as a directed acyclic causal graph. To make this more intuitive, consider the hierarchical equality task as example. In this task, 4 input numbers are provided. The first 2 and the second 2 numbers are each tested for equality, and the results of these 2 tests are then compared for equality themselves. For example, consider the input 1, 9, 6, and 6. The first pair 1 and 9 are not equal, yielding false, while the second pair 6 and 6 are equal, yielding true. Comparing these two equality results, false and true, gives the final output false, since they are not equal. An intervention on this causal graph could, for instance, involve severing the incoming connections to the first equality node and manually setting its value to true. Now let us discuss what a tau abstraction is. Suppose we have assumed algorithm represented as a causal graph. In addition, consider a neural network for which we want to determine whether the algorithm is a T-abstraction of the network. Let Fn denote the function implemented by the neural network and Fa the function implemented by the algorithm. Now assume an input x. For a tau abstraction, there must exist a surjective function tau x that translates the input of the neural network into the corresponding input for the algorithm. Causal abstraction defines the equality between a neural network and algorithm in terms of interventions. Let us therefore perform an intervention on the neural network, as illustrated here. We now require the existence of a function that transforms interventions on the neural network into corresponding interventions on the causal graph. Let us denote the inner node as psi int and the inner nodes of the causal graph as eta int. Finally, we require a surjective mapping tau that aligns the values of psi int with those of eta int. Now that all key terms have been introduced, we can express the condition required for causal graph to constitute a tau abstraction of the network. This means that for all inputs x and for interventions given the given intervention set, performing an intervention on the neural network and mapping the resulting inner nodes values to the causal graph must yield the same values for the inner nodes as first translating the inputs to the causal graph's input and then applying the corresponding mapped intervention on the causal graph. We can now define which holds when this equivalence applies for all possible interventions on the algorithm. Let us now note that in principle, any type of intervention on the neural network is permissible. To refine this, we introduce the concept of constructive abstraction. This is a strong tau abstraction in which each node in the causal graph is assigned a distinct non-overlapping set of neurons, as illustrated here. This constraint modifies the required mapping function such that each neuron is associated exclusively with a designated neuron set. The way in which we map nodes to neurons in the DNN implies different assumptions about how the network encodes information. In this example, where a set of neurons corresponds to a single node, we assume the privileged basis hypothesis, under which information in the DNN is encoded within subspaces aligned with individual neurons. Alternatively, there is a linear representation assumption which posits that hidden neuron dimensions need not directly represent concepts. Instead, concepts correspond to dimensions within a linear transformation. To implement this within our causal abstraction framework, we first apply a reversible linear map referred to as the alignment map, denoted phi, This allows us to obtain a latent space. Those dimensions can then be assigned to specific variables. Once these dimensions are defined, we can intervene on them directly by manipulating the corresponding latent dimensions. Finally, we map the modified latent representations back into the model's hidden space using the inverse of the alignment map, and continue the forward path of the network to obtain the final output. Under the privileged basis hypothesis, the alignment map phi is a permutation of the identity matrix, which implies that individual neurons themselves can represent distinct concepts. In contrast, the linear representation hypothesis assumes that concepts are encoded within linear subspaces. For a nonlinear representation hypothesis, the alignment map phi is a reversible nonlinear function, such as a reversible neural network, for example, a RevNet, reflecting that there is no inherent reason to expect features to be linearly encoded. Building on this, we introduce distributed abstraction, which is a strong tau abstraction in which the nodes of the causal graph are mapped to non-overlapping partitions of the latent space dimensions produced by the alignment map phi. So how do we find these distributed alignment maps in practice? The most prominent method is called distributed alignment search, or short DAS. Let's start with a dataset sample that includes a base input, along with two source inputs that define the interventions. Each source input corresponds to a separate run, both in the algorithm and the neural network. For the base input, we run the algorithm and network up to an intervention layer. At that layer, we intervene, then continue running both systems to completion, where we calculate a similarity loss, for example, a negative log probability, and apply backpropagation to train the alignment map phi, while keeping everything else frozen. In some samples, we have only one or the other source input, which means that we intervene on only a subset of the variables. To measure how well the algorithm and the neural network align under the map phi, we use interchange intervention accuracy, which measures the percentage of matching behavior between them under intervention. We can now introduce our final concept, the input-restricted distributed abstraction. This refers to a distributed abstraction composed entirely of input-restricted interventions, where each intervention can be constructed from values of other input-restricted interventions. An example is shown here, where we replace certain values with those from another input. On a high level, if an algorithm is an input-restricted distributed abstraction of a network, there exists a reachable latent space with some bijective alignment map, where the different dimensions are assigned to only one or non-variable, behaving under input-reachable intervention values as expected under the causal graph. It can be seen as a formalization of distributed alignment search. That concludes the background on causal abstraction. Let's now move to the nonlinear representation dilemma. The main theorem shown in our paper states that under specific assumptions, any causal graph can be shown to be an input-restricted distributed abstraction of any neural network. Now let me give the assumption required for this theorem, aligning any causal graph with any neural network, using some phi to get a latent space for input-restricted distributed abstraction. We assume that each node in the causal graph can be associated with at least one neuron in the model. Furthermore, both the algorithm and the neural network are required to solve the given task and to operate over countable inputs. Finally, the neural network must be both injective and surjective. To provide some intuition for how we prove the theorem, let us first fix the mapping from the input nodes to the input neurons as the identity function. For the mapping from the output neurons to nodes, we use argmax. We then only need to demonstrate the existence of an alignment map phi, such that there exists a tau prime between the remaining neurons and nodes, while preserving the correct output for the argmax mapping. To achieve this, we first leverage the countable inputs to define phi as injective in each dimension. We now consider an input-restricted intervention and account for the input injectivity. We then observe that both nodes in the latent space can identify which input caused their activation. This enables us to define a suitable tau prime, using this information to determine the corresponding values in the causal graph. If we now also leverage the output surjectivity, we now know that there exists points in the hidden space that produce the correct argmax when passed through the remainder of the neural network. By combining this with our knowledge of which inputs generated these latent space points, we can define the inverse of phi accordingly. This results in the required model outputs for argmax. We note that we only showed it here for one layer, but this can be extended to multiple layers by induction. We can assume for the previous layers these properties, and then prove that interventions work the same in the DNN and algorithm layer by layer. We now evaluated this theoretical finding in practice. For the algorithm, we use the previously presented hierarchical equality causal graph and test for the two equality variables eta inner 1 and 2. For the neural network, we employ a multi-layer perceptron with a 16-dimensional input followed by 3 hidden layers with 60-dimensional hidden spaces, and a 2-dimensional output trained on this task. Each node corresponds to a group of 4 neurons in the neural network's input layer. We then train phi with DAS to extract a suitable latent space of each of those hidden layers and used intervention sizes to finally compute the resulting IIA. By assigning the first 8 dimensions to the first inner node and the remaining 8 to the second inner node for interventions, we observe similar IIAs across the 3 different used alignment maps. Intervening on only 2 nodes for each variable already reveals bigger differences, where the weaker alignment map, based on the privileged basis assumption, no longer performs that well. Intervening on only a single dimension per variable shows performance losses in all alignment maps, except for the strongest, the nonlinear alignment map. We now perform the same evaluation across the remaining 2 hidden layers to gain our first K insight, using linear alignment maps. The IIA decreases with each layer, suggesting that the 2 inner variables are most likely encoded in the earlier layers. However, this pattern does not hold for the nonlinear alignment map, which shows nearly perfect alignment across all layers, contradicting the earlier intuition. In a second experiment, we examine how the IIA evolves during training. As usual, the DNN's performance increases over time. When applying the linear alignment map trained with DAS, we observe that IIA closely tracks the DNN's accuracy. However, using RefNets as alignment maps trained with DAS, with increasing complexity, this correspondence no longer holds. Most strikingly, with the most complex RefNet alignment map, we observe over 80% IIA, even when the models is randomly initialized and untrained. This demonstrates that a high IIA, which would normally suggest that the algorithm is an approximate input-restricted distributed abstraction of the model, can be misleading, as a randomly initialized model has not actually learned any algorithm. We then present in our paper experiments on large language models. For this, we use the task of indirect object identification. For this task, we apply the following algorithm. We begin with a prompt, such as friends Joanna and Christy found a mango at the bar, Joanna give it 2. We then can assign labels, for example Joanna as A and Christy and B. This allows for 2 possible completed sentence structures, ABAB or ABBA. In our example, we have an ABAB sentence. This information then can be used to determine the correct output, which in this case is Christy. An example for an ABBA sentence would be obtained by swapping the last Joanna with Christy in the prompt. We now evaluate whether the transformer model family Pythia aligns with this algorithm. Transformers take a string as input, tokenizes it, passes it through an embedding layer, then through several transformer blocks, and finally applies an embedding to produce the output. For the experiments, we apply an alignment map to the residual stream of the last token. Examining the IOI task performance across different Pythia models sizes, we observe that even when trained, the 2 smallest models fail to solve the task. When randomly initialized, none of the models can solve the task. Using a rotation map as the alignment map and intervening on the first half of the latent space and trained by DAS, we find that the resulting IIA again tracks the performance of the model. This pattern again does not hold for the nonlinear alignment maps. Even though both the trained and untrained versions of the two smallest Pythia models fail to perform the task, we still observe near-perfect IIA when using non-linear alignment maps. Evaluating this on the training process of a Pythia model, we see behavior similar to the previous hierarchical equality task, where near-perfect alignment is found even at random initialization. Therefore, we see that causal abstraction alone is not sufficient. It is crucial to balance the complexity of the alignment map with the observed IIA. Highly capable alignment maps can produce near-perfect accuracy even if the evaluated is not actually implemented in the model, and overly weak alignment maps may fail to detect the encoded features. The other notes that our theoretical proof effectively corresponds to a strong overfitting. To testing the generalization of discovered alignment maps is essential to detect gerrymandered alignment maps, which we exploited in our theorem. Looking forward, it will be important to continue investigating how feature representations are encoded in order to avoid using alignment maps that are too weak or too strong. Now to conclude this presentation. We are able to answer the central question of our paper: is causal abstraction enough for mechanistic interpretability? While promising, current causal abstraction is not enough. Multiple weaknesses need to be addressed in future work. That concludes my presentation. I hope you were able to follow along with at least parts of it, and I'm now happy to take any questions.
Yeah, I guess if no one is asking questions, I can say something. Yeah, I don't think I completely follow all of it for only the presentation, but I do think I got some idea what it's about. And like the first kind of the theoretical result, I also didn't completely understand it, but it seems like the kind of thing where you can make some theoretical result, but that in practice there is some more structure to the abstractions where I guess that's partly what you were saying, and like I feel like I have some skepticism of that kind of theoretical result in general, and the empirical thing where you show that in practice you can find with some non-completely arbitrary non-linear thing, you can find fake representations on actual neural networks. It's more like compelling.
I think, yeah, Dennis, go ahead.
What you, if I understand you correctly, the theoretical part actually is something which is somehow relying on some gerrymandered alignment maps, which in practice, for example, distributed alignment search does train on one set and then test on one other set. So our theorem actually does not show that it will work on some untrained data, for example. It is just showing that we can make, and therefore it's more an existence proof. So for any kind of data, we have we can show that there exists some alignment map which says that this causal graph is actually implemented by the model, even though it does not need to be implemented. But the empirical experiments actually show DAS, which is trained on some the train data and tested on some test data. So our theorem actually does not really doesn't give great guarantees in that setting that we actually find something which will generate to test data. And we actually also were quite surprised that we can train on one set and test it on another set, and there's actually then it works. So the alignment map still results in interventions which are behaving as we expect to, even though these data points are never seen. And that is actually something which we followed up with some future research.
Also, maybe Victor, to kind of go into this a bit more. I think so. Why the theoretical part matters a lot is because causal abstraction or distributed alignment search is very much built on a set of theory. And we basically show that this theory breaks down if you don't make assumptions about your abstraction map, which in a very high level intuitive thing is just the thing that maps from the network to your causal graph. Right? Distributed alignment search is basically you think, oh, my model implements this algorithm in this causal graph, and then you want to see whether you can find a map from the network to your causal graph that actually correlates with this. And we show that if you...
Sorry.
Yeah, go ahead. Go ahead.
I was saying the thing I'm wondering is more, is this, how much this is just the kind of result, like, you can have, there are infinite models that you can show that there are infinite models that for some input, like for some set of inputs and outputs have the same, there are infinite models that have the same result, but in practice, there are some reasonable, like things like neural networks works because the actual things you have in real life have some structure where you can actually have some assumptions that they are simple or something, and that works. I wondering how much this is the analogous results where you can show that there is always some graph that is equivalent, but maybe the graphs turn out to be like when you are having path assumptions, the graphs that are equivalent are super complicated or something.
So I think the point here is not that you can always find a graph that is equivalent to the network, but the other way around actually. The point is that any graph that you choose can be shown to be equivalent to the network. Which is, right, this is what causal abstraction or distributed alignment search kind of promises, right? It promises that if you claim, I think my network is doing this, and then I apply causal abstraction theory and distributed alignment search to evaluate whether my network actually does this. That's what it does. But we show that if you don't make assumptions about how things are encoded, then this breaks because you can show that any algorithm is implemented in any network. So it's kind of the other way around. And this matters for the causal abstraction theory because this is what it promised initially. It promised to give you a theory that if you have a graph, it can tell you whether it's implemented in a network or not. And so far, people have just always assumed that everything is encoded linearly. But now, more recently, this has been a bit more in discussion. I personally, I think most things are actually encoded linearly, but it's just we need to discuss how things are encoded in a network. And if you just state that we don't care how it's encoded, it can be highly nonlinear. We just care about whether this algorithm is implemented. Then our paper, our theory, and also our empirical results show that distributed alignment search and causal abstraction breaks down without any additional analysis. I hope that helps a bit.
Yeah, I think that makes sense. I also already had the impression that this kind of automatic search was much dependent on people on papers were first doing things like just use neurons, and later, they started using sparse encoders when that got popular. I just feel like a lot of it depends on how exactly you divide the model to do interventions. And people are going to have to figure out some better, like what exactly features are and how to divide the model if they want to get And yeah, I think your result is a cool. It's interesting.
I think
that.
so if you want to abstract it even more, I think it's just you can maybe even make some claims about interp in general, which is just if you're optimizing something in your interp method, you need to be really careful about what assumptions you make and what assumptions you don't make, and whether making or not making these assumptions breaks down anything in particular. For example, here, if you don't make the linear assumption, the theory breaks down. Like you don't have to do, it doesn't make sense to use thus if you don't make the linear assumption, at least in its current state, without analyzing generalization or something like this. Yeah.
Yes,
So yeah, go ahead.
Yes, and as Julian said, there is research out there which suggests or already shows that some features are nonlinear encoded. So that is actually what we call why we call it the nonlinear representation dilemma. So we have on one side, if you are just using linear maps, you on one side mitigate this problem which we have shown here, so you cannot really gerrymander the alignment map, but on the other side there are features which are encoded non-linearly. So if you're just using linear alignment maps, you will not be able to find them, and that is this dilemma. So the question, one thing is actually the generalization, how well does it generalize, and the other thing is other discussion, what kind of encoding do we assume in the model? Is that, as example, there is some work which shows that weekdays are encoded in a circle in a neural network. And so the question is how to
the addition thing.
Yeah, and as the question then of course becomes how do we select the right alignment map to on one side prevent such gerrymandered features, on the other side to prevent them and still get the correct encodings. So that is. And I think the authors are agreeing that causal abstraction is actually quite promising, but as we showed in this work, there's still a lot of work to do in case of generalization testing, and also on figuring out how complex an alignment map has to be, which is surprisingly actually the predecessor of causal abstraction can be said to be probing, and this probing actually had the same problems. How strong do we probe for something? And so what is also shown in this work is actually that the problems which were shown in probing followed causal abstraction, so there's still work to do. We cannot just assume it will, when it finds something, that it's automatically saying that it's encoded. So that is actually what one of the takeaways of this work is. There's still work to do to
like in probing, you don't like probing is usually a bad idea to use something like a neural network for the probing instead of a linear probe, because then you always get good results because your neural network figures out the thing you were trying to figure out, it was represented there.
Yeah, especially if your network is injective, right? Which there was just this paper.
Yeah, a new paper thing, I saw it.
Yeah. So, okay, there's quantization, which is a problem. They assume continuous states, which we also. But if you assume it's mostly injective, then as you said, if you have a highly nonlinear probe, it can basically deduce the whole input, so you can make any conclusions about the input. So you cannot really make any conclusions about whether things are truly encoded in a network or not with a probe here. You have this trade-off.
Yeah.
Exactly, and causal abstraction actually tried to alleviate this problem in probing by also requiring that the outputs behave under interventions as expected, which probing just tries to find out if is it encoded, and causal abstraction tries to figure out also when we intervene on this feature, does it behave as it should be given our assumptions what is implemented as algorithm. And what actually is then shown here, that the problems still come up, still too strong alignment maps still allow for figuring out things which are not there by simply gerrymander this whole thing. So figuring out what is the feature and then figuring out where it should put it. So that is actually the main proof that is possible even in causal abstraction.
anyone else want to ask a question or something? Because I don't want to be. I can ask more things, but I don't want to be just talking. If everyone
Hello. Well, thanks for the presentation. I had a question. Maybe it's a follow-up on what you just said. It's do you have any hint on what would be a good methodology to
Maybe I
make the
could
difference?
maybe I could ask something, Dennis. So
I think
if like I want to use DOS to analyze my network, how would you go about it now? Like knowing this result? What's your
think, yeah.
can you hear me?
Yes, sure. There is, I think, two people ask at the same time a question. But yeah, I think the
Yes.
question is the same one. Is the question the same one? How to use distributed alignment search and these methodologies to still get used?
I don't. Maybe there is some connection issue on my
I didn't
side.
hear the
Maybe
other person, so I don't know.
There.
Yeah.
Okay, I think I will go first with Julian's question and then with your question. Is that fine? Because I already heard his and I'm not sure if I heard you completely.
Okay.
But
yeah, I did hear you, by the way, so I don't know.
Yeah, okay. So right now, with the insights of this paper, the best suggestion I can give to still use the framework of causal abstraction, which, as I said, I still think it's highly useful, is for now to if you just want to get a short view on it, stay with rotation maps. You might not find the feature even if it's there, but at least you will not find some. You might get some false negatives, but at least you don't get. At least it's very unlikely that you get some false positives. If you want to dive deeper into and also find features which may not be linear, the best suggestion I can give you is probably the same as I did after this work, is to apply this with alignment search with some alignment map you think could be useful, and then analyze what actually is found. So make some visualizations to figure out what actually happens what actually is found as encoding of the feature. But if you're just wanting to apply it, the suggestion is stay with rotation maps. They are not that vulnerable for false positives. So you might get some false negatives, but if it's positive, it is possible that it's implemented. It's much more likely than when you use some strong alignment maps. Does that answer the question?
Yeah, sure.
Great. Okay, then your question.
Yes. Sorry. Maybe there was some misconnection. My question is maybe a bit of the same, but it's: do you have any idea on how could be what would be a good way to distinguish between what would be something that is too strong, where assumption too strong, where the probe or the alignment map does the heavy lifting, and something that is really inside the network? Do you have any maybe idea about analyzing the volume that you can get out of this, or some assumptions that would be good that is stronger than linear features, but maybe could be inside the network?
That's a good question. I have that is actually concerns probably follow-up work, and so there are two directions which we can follow. One is, for example, there is some work in probing, which just allows probing maps which are equally strong than the remainder of the model to find the input, so to say. So it's dynamically adapted to the model and where you look at the model. That would be one direction which could be interesting. So using alignment maps which reflect how much the model actually can the processing capabilities of the model after the layer you look into. On the other side, actually, we made some follow-up work on this and analyzed actually what is found when using a RevNet on the arithmetic task of the mechanistic interpretability benchmark. That's just some task which we have as a prompt, some summation, and then we look at if there's the carry-on feature. The carry-on feature in summation is the first digits of both numbers together and they are higher than 9, probably as you learned to add in school on paper. So then we looked at what is found by RevNet, and then we actually scaled down the complexity to figure out what actually is found, and we actually found that even linear alignment maps, so there is 2 different grades of linear alignment maps. In this work, our linear alignment maps are rotation maps, so they are a bit more constrained than just linear alignment maps, but we called them linear maps because also in the previous works they are called linear maps. But if you use the linear maps, which are interventional, so they don't need to have just the properties of rotation, but can be any other form which is possible by a matrix multiplication. And we actually are in that work, we can show that even then there is a possibility that the model is exploiting some other feature and doesn't really return something faithful. So if you want to get out of just using rotation maps, which allow to mitigate such things which we saw there. So rotation maps is relatively faithful just because it is so constrained that the alignment map cannot really hack too much, so to say. But if you want to go even just to linear maps, which are probably the simplest mapping which you can have after rotations, even then you already run into problems that you can find something which actually is not existing there. So my suggestion is if you want to apply anything more complex than linear alignment maps, you probably have to get your hands dirty, so to say, and figure out what actually is found and analyze it. And that actually can right now be a bit of process. I spent 2 months just hunting down one feature, this carry-on feature, to figure out what it actually is doing. And so my suggestion right now, if you don't want to spend 2 months just to figure out what you found, then probably just stay at rotation until there are improvements made to causal abstraction, which allow to prevent such behavior. I'm quite confident that there is such improvements. I also talked with Atticus Geiger, which is the original author of distributed alignment search, and he also is aware of this, and there needs to be some improvements. So that, and on the other side, one other direction which can be used besides looking what is found is on the other side also improving generalization methods, so to say. So try to figure out if the feature actually the feature you found actually transfers from your setting to more out of distribution settings. That is something else which could be useful. So either stable rotation maps, if you want to spend a bit more work, try to experiment with as much test data which is as out of distribution as possible. That is probably the middle ground of work versus work quality trade-off. And if you want to be quite sure what you found, you probably have to go in there and spend some time figuring out what you found. Does that answer the question? Yes, yeah, that's actually also a good point. We actually showed that it follows it. That's actually the intuition which we had first why rotation might could be. There's still the problem with rotation that it will just find linear maps and they need to be orthogonal to the other features because it's just rotation. So you have to find something like you can just find something like that, and that actually the dilemma part comes in. There is enough work which shows that some features are not linear, and you will not find them when you just use linear alignment maps. It will not work. So, as said, if you just want to get some fast results with thus stable rotations, it will give you some false negatives probably, but at least it mitigates many false positives, and that's probably also the reason why in current research rotation maps actually are seemingly faithful, because they simply they are so restricted that exploitations of different structures is just very hard. Thank you for the question, by the way. Are there any other questions? I'm happy to answer any questions which are there.
Okay.
I have
I
a
guess-
minor thing to ask if nobody else asks anything else. Yeah. So this is not very important. But you earlier mentioned like the days of the week being on a circle as an example of a non-linear feature, but isn't that still a linear representation? Like there is some structure there that you wouldn't find on something like sparse encoder, but each weekday is still a direction on the circle, right?
Yes, but it's in the hidden space. It's still you cannot draw any line through this, any line which actually represents the days, so to say. So if you are drawing a line through a circle and then project it down, the circle down to the line, there will probably be overlap between different days which are on opposite sides of the circle. So it is a direction, so to say, but it's a direction in rotation, and to find a direction in a circle and to find such directions, you need some more complex alignment maps, which are given in that paper actually. So, but to find the alignment maps which are mentioned in that paper, you actually all know not linear. They are all having this circle geometry in it. By the way, that paper actually got an update, and it's no longer a circle. It's still a circle, but a circle-like structure in more dimensions. So it's not just a circle.
Okay.
Also,
Yeah,
maybe the intuition here is like the day is still linearly encoded, but the relationship between the day is non-linear. So like Monday is still clearly linear direction.
Yeah, I think
But then the relation
related in that on the paper, Anthropic paper, where they do there is a paper where they found how GPT a bunch of models, it was PC and the thing at GPT-2 and whatever, like did addition, and they found it with something similar to the modular addition thing that Neil found, but with some kind of helix structure. And there is the Anthropic paper, I don't remember right now, the one where they found a bunch of found a bunch of graphs of like features, how they try to find some algorithms by looking at features, and it feels like the one where they do they explain addition and they get a bunch of complicated things with modulos and whatever. Seems like that might be what happens if you like it looks vaguely to me, maybe I just wrong. It looks like what you take if you have something like the helix structure thing, and you are taking linear slices from it, and it's trying to explain a single example of addition, and they might just be missing like the complete thing with the whole structure.
I didn't fully get it, but yeah,
I
can you
think
maybe
that's some
repeat?
weird idea I had, like when I was reading that paper for a previous reading group. Sorry.
Okay.
Yeah, I think we also read this helix paper where they showed this helix. But yeah, we actually also, at some point in the remaining time of my master's thesis, actually we looked also, we had some hypotheses, at least I had some hypotheses, that maybe what is found is some way of cutting through the true feature when we're using just linear ones. But yeah, it didn't turn out to be that. But it was about the carry-on feature in the arithmetic task, which is summation, so to say.
Yeah, I guess that my idea is just that it seems likely that in addition, specifically, bigger models the do something like the helix thing, but methods like the methods that are used, they just use sparse encoders to find linear encodings can't find that kind of structure, and like the things like the anthropic paper where they things like where we're just looking at graphs of linear how linear features do cause some output might just be missing that kind of nonlinear representation of addition or of numbers or whatever. It seems related, but not
Yeah,
super sure either.
yeah, I think I see your point. That's true. Sparse autoencoders, that's also something I saw, actually are not able to find anything which is nonlinear. At least in the papers I read, they always used some kind of linear mapping, a linear encoder and decoder, so to say, with a RevNet activation function before the hidden space. So they probably also not find, they will not find any rotation. That's actually also, yeah, I agree with that completely. And there is also the other question, of course, does a large language model actually do any computations at all as we use them, for example, on writing huge summations down on paper, or are they just some kind of memorization machines which just picks out the right place, the right answer? And there's also work which suggests that large language models are some kind of something in between, some kind of heuristic machine where they have different features inside of them, where some features in some cases push the output in the right direction, so the tenths and the first and the second digits and so on. So it's still an open question actually how it is encoded, how addition actually is encoded in models. And as far as I see, there's still no consensus on how it's done. And also in my work here and in my work which followed after this, there was not really any, there is no clear answer to this. So causal abstraction right now cannot give any answer to the question of what actually is done in summation. It's still, as I want to repeat, it's still a very promising method, but it just needs more work on it. It's to get to iron out these problems, because right now it is, as far as I can see, it's more applied with the thinking. It will just work because it's causally correlated, so it does actually what we think it does when we intervene, and so then is the thought, then we actually found something, and my work so far shows that while there's still work needs to be done to actually that we can and say we actually found something the model actually is doing, and not just something the alignment map is exploiting some other things in the model. I hope I deviated with that answer not too much from your question.
I guess I just was thinking about like how like in this in this I should share my screen. This attribution graph in the Anthropic paper seems to me like the kind of thing where I wonder if this is common, where so they are doing the attribution graph for like some specific addition, right? And they get I accidentally moved the and they get all of this. I feel to me that this might just be this explanation here might just be taking a linear slice of a more complicated and some non-linear thing in terms of there you find things like some feature that represents the number mod something and things like that. And that seems like the kind of thing you might find if you are if the actual representation is something like a circle or something like the helix from that paper, and you are just taking linear slices from it, and you find things like all of the numbers that end in 5 are in some direct, are some activate some feature in some direction because the actual thing is some kind of helix and it has a module of 10, so it happens to be pointing in the same direction every all the numbers that end on 5 and something like that. And that's just that kind of thing seems related to all of this.
Yeah, I agree. This seems reasonable that something like this could be happening. Although it's also not sure what. Yeah, we just don't know.
Yeah, I also agree. It's an interesting hypothesis. And as I said, as I saw in my work, it's not always what we see is not always what actually happens. So it actually could be something like that. That's actually also something which we discussed internally. That such interpretability methods and especially visualizations can actually include some kinds of red herrings which seem important or seem structurally, but in the end turn out to actually not be that important or actually be part of something bigger, like for example this cuts into this sphere. So that's a good point. So, and actually I also have here to mention probably that while I'm looking through literature, I never really saw I'm not really sure if there is any good definition of what it means for a found feature to be actually faithful. Most of what I found in this regard is actually a feature is faithful if our method finds it, or if it's causally related to the output or something like that. And as we showed, it doesn't really need to be faithful because we have these extreme cases. For example, we can find for a random model actually that it implements it, but the random model, of course, doesn't implement it, or we can find for any neural network, any algorithm. So the discussion of what is a faithful feature is probably still open, as far as I know. It's
part of the problem is actually figuring out what it means for a feature to be faithful. Because if we have some clear idea of that, we could already be doing things like testing, like figure out. It would be easier to get more to make better methods. Have some clear idea what it means for a feature to be safer that we can just test on new methods.
I'm not sure whether there's a solution to this problem. I think it's about you need to make assumptions, what you think, what you define as being faithful, and then you can do stuff with it. I don't think there's like a ground truth definition of a feature being faithful. How would this look? But I don't know. I mean, do you know the mechanistic interpretability is mechanistic interpretability identifiable paper, which kind of reminds me a bit of this discussion. Denis, I think you know it for sure. Diedos.
I think so, but yeah.
By Maxime Payard. I'll send it.
Great, then. Yeah, and in the end, I think the best, at least I can do is at least the best we were able to do is not to show what is faithful, but taking the definition of what causal abstraction gives us and then show that there are some situations which it intuitively seems wrong, that is the correct definition for a faithful feature. So in our case, it is that we can align any algorithm with any neural network, and that we can find for random initialized networks good IIA, so to say. Thank you for sending the paper. This everything, everywhere. Yeah, that's actually one I know. This discusses if if a feature which is found needs to be the only one, so to say, which encodes it, and only if it's the one feature which encodes it.
Yeah, it basically asks, it discusses this question that we also have been discussing of like, is there a ground truth feature, or is this just, can we identify?
I guess it seems to me like it's that there's probably at least some set of reasonable natural assumptions you can find in the same sense that in general in science these kind of questions people just find some reasonable assumptions that work a lot of the time, but I don't know.
Yeah, in my personal opinion is probably that's a question of iteratively refining the definition. For example, there was this recent paper from Atticus, which he took a more philosophical stance on it. And one of the important points there shown was that it needs to generalize, so to say. So it needs to generalize to all possible data. But of course, that is not testable in reality. But still, that is.
Sorry.
Yes.
Some people, I feel like some people like Neil lately are just. A method is good if it works on practical examples or something like that, and kind of gave up on having a super clear idea of what is truly represented on the model or something like that.
Yeah, I agree. So Neil has a much more practical view more recently. More his approach to making more recently is more of this thing of let's do something that has a direct practical impact. And while I think this is like very interesting and we need to do this because this is kind of in the end what interpretability should give us, but I still think there's like a lot of interesting, more theoretical problems to solve that will downstream also help us. But yeah, this is the normal problem of more practical applied research and more foundational theoretical research.
Yeah, at the same time you do like find a lot. Like you do find solutions to more practical research by thinking a lot, by doing more base research and thinking about more the philosophy of it and things like that. That also happens. I don't know what's best in this case. Probably better if
I
we
think
have
both. We should
yeah,
do
people
both.
doing both. Yeah.
Yeah, I also agree. Here is, by the way, I send in a chat the paper from Atticus, which takes a more philosophical question on how causal abstraction is showing faithful features. I found it quite interesting. Great. And yes, also, I agree that it probably is necessary to do both, because on one side, theoretical can help practical applying of it to find, so to say, more better features or more faithful feature, whatever that means. And on the other side, practical appliance will also then give some insights, for example, insights into how what theoretical parts by now ignore. So yeah, as example, I made some experiments which are quite practical, which are just trying to find a feature and then figure out what this was found, and that also informed some of that is also quite informative of how to improve causal abstraction theoretically. So don't give up on either of them, neither theoretical nor practical. Neither of them are not used. Both are very important.
Agreed. Okay, guys, I slowly have to leave, but thanks a lot for having us. Yeah. Bye, guys.
Goodbye. Still around for questions if there are any.
Anyone else want to ask some question? I think for me I can end it here, but yeah, that's.
Yeah, if for me it's fine as well, but if someone has questions, also feel free to ask later on some questions. I think you
Oh, by
find.
the way, I probably should have said it earlier when there were more people, but people who are here, I made a when to meet for like the reading group, when people are available for the reading group, because I might change it after this week. So people should just look at that and put them when they are available. If you want to be on the reading group in the future, because I probably change the time in November.
Gotcha. Victor, just a quick something. So I am finally revived because I'm now in the EU. So do you still want to work on like the chess project?
Oh, right. We can talk later about that. Yeah, I was working on something else because I got a grant. So, but I might still want to do a bit on the. Yeah, I just been busy, but I'm fine with. We can talk one of these days about the chess project and maybe do something. It's not like I've been that productive on the other thing, to be honest. But yeah, I was more the. I was supposed to be working on the other thing, so I wasn't thinking about other projects.
Yeah,
but I
okay.
also was not being that productive working on the thing I was supposed to be doing. So I've been doing things, but not all. It's not like I don't have free time anyway. So
yeah. I mean, yeah, that makes sense. It sounds like you know the usual kind of struggle. Yeah, okay. I text you on that chat channel later then. All right. See ya.
See ya.
Bye.
Okay.